Now, we're all scientists, and as fun it is to speculate and think about all these crazy, weird thought concepts, we also want to make sure that we have some experiments, some data to support these ideas, because there's no point of these thought experiments if they don't help us understand the universe, help make predictable observations. So let's go over some. This is a small fraction of the different types of experiments that is evidence in support of the idea that relativity is a thing. Now, for starters, speed of light. Every experiment anyone has ever done has agreed that the speed of light is constant. You want to disprove relativity? Find something violating the speed of light. Other consequences. Let's look at this image here. Einstein, not only did he mathematically describe this curvature of space-time, he also said, here are some facts, some predictions that had to come out of it. And one of them was perturbations on the orbit of Mercury. Basically, as Mercury orbits the sun, because of the gravitational pull the sun has in the space-time around it, Mercury's close enough that it should feel this extreme gravitational effect that's not just Newton's law of gravity. And that will result in these additional orbits. This is what we call the perturbations. So, one thing is that these changes to Mercury's orbit is not predicted by classical mechanics, classical physics, Newton's laws. And, in addition, people had already measured this. Before Einstein had even come up with relativity, people were measuring, hey, Mercury's doing some extra weird orbits as it's going around the sun. So people already knew about this, and Einstein used that as one of his first steps in arguing to the scientific community, hey, I have a valid idea here. I can explain something that none of you can. Furthermore, Einstein said, all right, Mercury's orbits, like celestial mechanics, you could try and come up with another thing. So I'll come up with one that you can't get with just orbits. He looked at a concept called gravitational lensing. Here's the principle. There is a star. Oh, switch colors. Let's switch to that. Right. There'll be a star here, and it's radiating light this way. Now, if relativity isn't a thing, if space-time distortions isn't a thing, what this light should do is just keep going straight. But Einstein said, hold on a second. If the light coming from that star passes through the space-time curvature of the sun, large massive objects distort space-time, then instead what should happen is that starlight should deflect. It should bend and not follow the straight path anymore. So Einstein predicted is that if you look at the light near the edges of the sun, you'll see it change in direction. You'll see a deflection due to space-time warping around the sun. Well, people didn't have to wait too long to test this idea. They waited until the next solar eclipse. Because of the proximity of the star to the sun, because of the proximity of that star to that sun, you normally just wouldn't see the bend in that starlight because there's this bright object blocking our view, our own sun. But astronomers just waited until the next eclipse, and it came not too long after Einstein predicted this. 1919 was the next solar eclipse. And so astronomers set up to say, look, I know which stars are going to be behind the sun, and let's measure the deflection and the angular position of the stars. Can we get this angle deflection? Turns out it was about 2 arc seconds. Can we detect this? And they did. And with these photographs here, with these photographs like this, that's when Einstein blew up in terms of this idea of relativity, and it's widely accepted now because the evidence was there to support it. So these are experiments that are actually about a century old now. Let's start moving to some modern experiments. Here's a great one. Moving clocks go slower. So here's two clocks. One's stationary and the other one's doing some circular orbit around them. And they have the clocks winding away, right? Well, the one that's in motion relative to the blue clock, the red one, time should go a little bit slower. Remember that time dilation. So here's a simple experiment. Make a bunch of clocks. Send a couple of them on orbits around the planet and see what happens to their time. Do they synchronize or is there a delay created? And with that simple concept of trying to take into account the time dilation of two synchronized clocks, you get the Hafele-Keating experiment. Absolutely love this. Here's Hafele and Keating, all right, and a stewardess on an airplane. And here's what they did. They built 3 atomic clocks. Why atomic clocks? Because atomic clocks are accurate enough up to nanoseconds. They can measure time out to the nanosecond scale. And here's what they did. With 3 clocks, one stayed in the laboratory. The other 2 went on flights around the planet. Imagine pitching that to your advisors. Yeah, I'm going to need some money. Why? Well, I need to fly a clock around the globe. That's what they did. One clock flew in an eastward direction around the globe, and then they did the experiment again, got another clock, and they flew westwardly around the globe. And when they were said and done with these literal global round trips, they brought all 3 clocks back into the same lab and compared how synced up were they in terms of the time that had transpired. And what they found was that a clock that had flown eastwardly, it was about 60 nanoseconds behind the lab clock. The one that had flown westwardly, it was 273 seconds ahead of the laboratory clock. And this was in strong agreement with relativistic predictions. One went ahead, one went behind because, well, Earth's also rotating. So when you calculate your time dilation, you have to take into account the motion of the airplanes and the motion of the Earth. But either way, this simple experiment here, comparing the synchronicity of these 3 atomic clocks, was further evidence confirming Einstein's theories on relativity. You start to go to modern day stuff. We're surrounded by satellites. Heck, an insignificant number of you are probably watching this video right now by streaming data off the cell phone plan, making phone calls. How does that work? Well, we launch satellites in orbit around Earth to help relay, communicate this information. And if you do not take into account the relativistic effects, the time delays or gain based on how high above Earth's surface is, you will get useless satellites. So our entire global infrastructure does not function if you do not account, if you ignore relativistic effects.